we're going to bump these two cars into each other. So what we want to see is that if I move this car to your right, then the result is another car moved to the right. I can try to do something harder. So this car is moving to the right. This is a little bit to the right. Or I can try, let's see. So in this case, this car comes to a complete stop while the motion seems to transfer from here to the other car. So what we see is that when this car originally moving to your right, bump into another car, there are some different possible results. We had seen that the result might be both cars going to the right. Both cars going to the right. Let's make this arrow longer. So that's first situation. Another type of situation is that the first car comes to a complete stop, and then only the other car is moving at the end. So this car comes to a complete stop, and this one is moving. So there might be another situation, which I didn't demonstrate, but it is possible, which the second car moves to the right, and the first car goes reverse. So those are the three possible situations, and I claim there's no other possibility. Do you agree? Yeah. Okay, good. So now these are all the possible results. What we see is that if originally the car is moving to the right, then at the end, something must move to the right. Either both of them are moving to the right, one of them is moving to the right, or one is moving to the right, but there must be something that keeps moving to the right if something is moving to the right in the beginning. So it seems like the motion of the block is somewhat conserved. If something is moving in this direction, then at the end, there must be something moving in this direction. And this motion has direction. It's not like energy. Energy doesn't care about direction. But in this case, obviously, moving to the right is important. You will not see any end or any final state that the blocks are moving to the left, because initially they are moving to the right. So this rightward motion seems to be conserved. So let's assume, or let's just say that it is conserved, and this rightward motion is called momentum. So here is our initial state. This is our final state. And we can do the same thing just like energy. For momentum, the total momentum is the momentum of the first block, I. We say we are conserving motion, and motion has direction. So we know momentum is a vector. conserved, in this case P1I, the initial momentum of the first block, plus the initial momentum of the second block, which is 0 in this case, but it doesn't need to be 0 in general. Then momentum conservation is just like energy conservation. The sum of the momentum for the two blocks should be conserved. It should equal to the sum of the momentum for two blocks. And it doesn't matter which state you are looking at. The initial momentum of the system should equal to the final momentum of the system. This is what we call momentum conservation. Let me check the camera. So, what is momentum related to? We know it's about motion, and it is a vector. Any vector about motion you know? Have you guys heard any vector about a object's motion? Have you guys learned any vector at all in this class?
Velocity?
Good, velocity. So let's assume momentum should be related to velocity. Now, let's look at another situation. So right now, I'm going to bump this car into this car. So this car is moving. If I push the car with the same speed, but now this car is heavier, let me try to push the same speed I was pushing. I hope you can feel this car is moving faster compared to without the extra weight. And this is without the weight. Do you guys think it is faster for a second car if this is heavier? Let's try it. I hope I have two rails. Alright, so boom. Do you guys see this is faster now if the initial car is heavier? So, of course, if the second car is moving faster, so this is the initial state, this is our final state. If in the final state the car is moving faster, then the momentum must be bigger. Okay? What we did is to bump into this car with a heavier cart. They are moving in the same initial speed. The speed is the same. But at the end of the day, the second car will get a bigger momentum if if the first car is heavier. Now, momentum is conserved. In this case, the first car gives all the momentum to the second car. In the second case, the first car did not give all the momentum to the second car because it was still moving at the final state. But even though the second car only received a part of its momentum, it is still more than the momentum for this case. Therefore, we know that this heavy block moving with the same velocity must contain more momentum. And the bigger the mass, the bigger the momentum inside this block. Okay? So we can guess that momentum is related to velocity. It is proportional to velocity, and the bigger the mass, the bigger the momentum. The bigger the mass, the bigger the momentum. So this proportional constant might be the mass of the block. And I'm going to tell you it is indeed true. If you try to look at the mass of the first block times the initial velocity of the first block, add that to the same thing for second block, this will equal to the mass of the first block and its velocity in the final state plus the mass of the second block with velocity in the final state. So if the sum of these two equals the sum of these two, you know mass times velocity is the momentum we're looking for. Okay? And again, I'm not going to prove it to you. It's tedious. There's proof in the textbook. If you're interested, you can go check it. For now, I'm going to ask you to memorize that momentum will be mass times velocity. Okay? So let's go back to these three cases. Let's say initially all the block is moving equally fast. So the initial momentum of these three initial states is the same. We start with the same initial momentum. So here, the first block shared its momentum with the other block. So because momentum is conserved, this block needs to share the arrow with the other guy. So these two arrows should be shorter than the first arrow. This momentum is distributed to both blocks. So both of them will be having smaller momentum than the initial block's momentum because you share this momentum with two. Okay? Now in this case, the first block